AFCI, or arc fault circuit interrupter, testers are known to sometimes fail to trip the breaker on long circuit runs. The primary reason for this is that these testers may lack the capacity to supply sufficient current needed to simulate a ground fault effectively, particularly on extended circuits. Consequently, even if the breaker itself is functioning correctly, it might not trip during the test. It is imperative that inspectors are aware of this inherent limitation of AFCI testers. They should not depend solely on these testers as the definitive method to ascertain whether a breaker is functioning as it should. In instances where an AFCI tester fails to trip the breaker on a long circuit run, it is crucial to employ alternative methods to validate the breaker's proper operation. One such method involves utilizing a ground fault circuit interrupter, or GFCI tester. GFCI testers operate by simulating a ground fault through the injection of a small current into the circuit. If the GFCI tester successfully trips the breaker, it serves as an indication that the breaker is indeed functioning properly. Another approach to verifying the correct functionality of a breaker is to use a multimeter to measure the resistance between the hot and neutral wires. A low resistance measurement signifies that the circuit is adequately grounded and that the breaker is operating as intended. When dealing with electrical circuits and protection devices, it's crucial to understand the underlying principles and testing methodologies. AFCI breakers are designed to protect against arc faults, which are dangerous electrical conditions that can lead to fires. These breakers are more sensitive than standard circuit breakers and are designed to detect the unique characteristics of an arc fault. The testing of AFCI breakers requires specialized equipment that can simulate these arc fault conditions. However, as noted, these testers have limitations. The length of the circuit can significantly impact the ability of an AFCI tester to function correctly. Longer circuits have higher impedance, which reduces the current that the tester can deliver to simulate a fault. This is why it's important for inspectors to be aware of this limitation and to use alternative methods to verify the breaker's functionality. GFCI testers work on a different principle than AFCI testers. GFCI breakers are designed to protect against ground faults, which occur when current leaks from the circuit to ground. These breakers are very sensitive to ground faults and will trip quickly to prevent electrical shock. GFCI testers simulate a ground fault by injecting a small current between the hot wire and ground. If the GFCI breaker is functioning correctly, it will trip immediately. Measuring the resistance between the hot and neutral wires with a multimeter is another useful technique for verifying the integrity of a circuit. A low resistance indicates that the circuit is properly grounded and that there are no shorts or other faults. However, it's important to note that this test should be performed with the circuit energized to prevent electrical shock. In addition to these testing methods, visual inspection is also an important part of verifying the safety of an electrical system. Inspectors should look for signs of damage such as frayed wires, cracked insulation, and loose connections. They should also check to make sure that all electrical components are properly installed and that the wiring is correct. It's also important to understand the relevant electrical codes and standards. The National Electrical Code, or NEC, provides detailed requirements for the installation and testing of electrical systems. Inspectors should be familiar with the NEC requirements for AFCI and GFCI protection, as well as other safety standards. When working with electrical systems, safety should always be the top priority. Electrical work can be dangerous, and it's important to take precautions to prevent electrical shock and other hazards. Always de-energize circuits before working on them, and use appropriate personal protective equipment such as insulated gloves and safety glasses. In summary, AFCI testers have limitations, particularly on long circuit runs. Inspectors should be aware of these limitations and use alternative methods to verify the functionality of AFCI breakers. GFCI testers and multimeter resistance checks can be used as alternative methods. Visual inspection and knowledge of electrical codes and standards are also important for ensuring the safety of electrical systems. Always prioritize safety when working with electrical systems. The operation of an AFCI breaker hinges on its ability to detect specific current signatures indicative of arc faults. These signatures are often characterized by erratic and high-frequency waveforms that differ significantly from the smooth sinusoidal waveforms of normal load currents. AFCI breakers' internal circuitry is designed to continuously monitor the current flowing through the circuit and analyze its waveform. When this circuitry detects an arc fault signature, it triggers the breaker to trip, interrupting the current flow and preventing a potential fire. The sensitivity of an AFCI breaker is a critical factor in its effectiveness. A breaker must be sensitive enough to detect even small arc faults, but not so sensitive that it trips unnecessarily due to normal circuit conditions. This balance is achieved through careful design and calibration of the breaker's internal circuitry. The length of the circuit is a significant factor that can affect the performance of an AFCI breaker. Longer circuits have higher impedance, which means that they resist the flow of current more than shorter circuits. This higher impedance can reduce the amplitude of the arc fault signature, making it more difficult for the AFCI breaker to detect. In addition, longer circuits can introduce more noise and interference, which can also mask the arc fault signature. For these reasons, it is important to consider the length of the circuit when testing an AFCI breaker. If the circuit is too long, the AFCI tester may not be able to generate a strong enough arc fault signature to trip the breaker. In this case, alternative testing methods may be necessary. GFCI breakers operate on a different principle than AFCI breakers. GFCI breakers are designed to protect against ground faults, which occur when current leaks from the circuit to ground. A ground fault can occur when a person comes into contact with a live wire and provides a path for current to flow to ground. This can result in a severe electrical shock. GFCI breakers are designed to detect even small ground faults and trip quickly to prevent electrical shock. They work by monitoring the current flowing through the hot and neutral wires. Under normal conditions, the current flowing through the hot wire should be equal to the current flowing through the neutral wire. However, if a ground fault occurs, some of the current will leak to ground, creating an imbalance between the hot and neutral currents. The GFCI breaker detects this imbalance and trips the circuit. The sensitivity of a GFCI breaker is typically 5 mA, which means that it will trip when the difference between the hot and neutral currents exceeds 5 mA. This is a very small amount of current, but it is enough to prevent a serious electrical shock. GFCI breakers are required in many locations such as bathrooms, kitchens, and outdoor areas. They are an important safety device that can protect against electrical shock. When testing a GFCI breaker, it is important to use a GFCI tester that is designed for this purpose. The tester will simulate a ground fault and verify that the breaker trips correctly. It is also important to visually inspect the breaker to make sure that it is in good condition and that the wiring is correct. Measuring the resistance between the hot and neutral wires with a multimeter is another useful technique for verifying the integrity of a circuit. A low resistance indicates that the circuit is properly grounded and that there are no shorts or other faults. However, it is important to note that this test should be performed with the circuit energized to prevent electrical shock. The NEC provides detailed requirements for the installation and testing of electrical systems. It is important for inspectors and electricians to be familiar with these requirements to ensure that electrical systems are safe and reliable. NEC Article 210.12 covers arc fault circuit interrupter protection. It specifies the locations where AFCI protection is required in dwelling units. NEC Article 210.8 covers ground fault circuit interrupter protection. It specifies the locations where GFCI protection is required in dwelling units. NEC Article 250 covers grounding and bonding. It provides requirements for grounding electrical systems to ensure that they are safe and reliable. NEC Article 310 covers conductors for general wiring. It provides requirements for the size and type of conductors that are used in electrical systems. NEC Table 310.15b16 provides ampacity ratings for conductors based on their size and insulation type. When working with electrical systems, safety should always be the top priority. Electrical work can be dangerous, and it is important to take precautions to prevent electrical shock and other hazards. Always de-energize circuits before working on them and use appropriate personal protective equipment, such as insulated gloves and safety glasses. In addition to the methods already discussed, there are other techniques that can be used to troubleshoot electrical circuits and verify the functionality of breakers. One technique is to use a circuit tracer. A circuit tracer is a device that sends a signal through a wire and allows you to trace the wire back to its source. This can be useful for identifying the correct breaker for a particular circuit. Another technique is to use a thermal imager. A thermal imager is a device that detects heat. It can be used to identify hot spots in electrical circuits, which can indicate a problem. When troubleshooting electrical circuits, it is important to have a good understanding of electrical theory and to follow safe work practices. Always de-energize circuits before working on them and use appropriate personal protective equipment. It is also important to consult the NEC and other relevant codes and standards. AFCI testers simulate arc faults by generating high-frequency noise on the electrical circuit. This noise is intended to mimic the electrical signature of an actual arc fault. However, the effectiveness of these testers can be affected by several factors, including the length of the circuit, the type of wiring, and the presence of other electrical devices on the circuit. Longer circuits tend to attenuate the high-frequency noise generated by the AFCI tester, making it more difficult for the tester to trip the breaker. The type of wiring can also affect the performance of the AFCI tester. For example, circuits with older wiring may have higher impedance, which can reduce the current that the tester can deliver to simulate a fault. The presence of other electrical devices on the circuit can also interfere with the AFCI tester. For example, electronic devices such as computers and televisions can generate their own high-frequency noise, which can mask the noise generated by the AFCI tester. Because of these factors, it is important to use caution when interpreting the results of AFCI testing. If an AFCI tester fails to trip the breaker, it does not necessarily mean that the breaker is defective. It is possible that the tester is simply not able to generate a strong enough arc fault signature to trip the breaker due to the factors mentioned above. In these cases, it is important to use alternative testing methods to verify the functionality of the breaker. GFCI testers simulate ground faults by injecting a small current between the hot wire and ground. This current is intended to mimic the electrical signature of an actual ground fault. The GFCI breaker is designed to detect this current and trip the circuit. The effectiveness of GFCI testers is generally not affected by the length of the circuit or the type of wiring. However, it is important to use a GFCI tester that is designed for the specific type of GFCI breaker being tested. There are different types of GFCI breakers, and each type requires a different type of tester. Measuring the resistance between the hot and neutral wires with a multimeter can provide valuable information about the integrity of an electrical circuit. A low resistance indicates that the circuit is properly grounded and that there are no short or other faults. However, it is important to note that this test should be performed with the circuit de-energized to prevent electrical shock. To perform this test, first de-energize the circuit by turning off the breaker. Then disconnect the hot and neutral wires from the breaker. Set the multimeter to measure resistance in ohms. Connect the multimeter leads to the hot and neutral wires. The resistance reading should be very low, typically less than 1 ohm. A high resistance reading indicates that there is a problem with the circuit. This could be due to a loose connection, a corroded wire, or a short circuit. If the resistance reading is high, it is important to investigate the circuit further to identify and correct the problem. In addition to the testing methods discussed above, there are other tools and techniques that can be used to troubleshoot electrical circuits. These include circuit tracers, thermal imagers, and voltage testers. A circuit tracer is a device that sends a signal through a wire and allows you to trace the wire back to its source. This can be useful for identifying the correct breaker for a particular circuit. A thermal imager is a device that detects heat. It can be used to identify hot spots in electrical circuits, which can indicate a problem. A voltage tester is a device that measures voltage. It can be used to verify that a circuit is de-energized before working on it. When troubleshooting electrical circuits, it is important to follow safe work practices. Always to energize circuits before working on them, and use appropriate personal protective equipment. It is also important to consult the NEC and other relevant codes and standards. The NEC provides detailed requirements for the installation and testing of electrical systems. It is important for inspectors and electricians to be familiar with these requirements to ensure that electrical systems are safe and reliable. Electrical safety is paramount. Always exercise caution and adhere to safety protocols when working with electrical systems.